I think we are, yes. So we're recording. So welcome to this is week 7 in the series. And so we did 4 weeks of data management. This is now the 3rd week of doing data analyses. And so we did kind of regression, advanced regression, some quantile regression, and then people had also wanted to do multi-level models. And so I think maybe by the end of this, depending on where we get to, how people feel, we can either kind of just stop with multi-levels at this part, because just remembering this is not a full class, right? This is a way to get exposure to how to specify these models in R. Now, there is a place for learning the analyses, but this is just to kind of whet the appetite, so to speak, on how to be able to run these models and different considerations of doing these types of models in R. So depending on what we get through, we could either say, you know, this is good for thinking about multi-level models. Let's move on to the graphing, because I know a lot of people wanted to do graphing, and we can kind of then do 4 weeks, which would take us through the end of August on graph and plots, and then we would be done with this. Or if people feel like, you know, it'd be great to do one more kind of lecture on multi-level models, we could do something where I've been thinking about, like, maybe intros to growth models in R, and that could be both multi-level and latent growth model perspectives, just kind of linear, nonlinear growth models, not curve of factor models, but just looking at individual growth curves using lmer and levon or tidysem. I haven't used tidysem yet, but that's an option, as well as maybe generalized linear mixed models, sort of multi-level logistic regression. So just keep that in the back of your mind as we're walking through this today, and we can kind of figure out where we want to go. And then last quick plug, as I've mentioned it before, two actually. So Betsy McCoach is getting ready to do her multi-level in R. So if you like what is here today, and it's like, but you're a horrible teacher, I want someone who actually is a multi-level model expert like Betsy McCoach, then I can kind of, I'm waiting on the information from her. She and I are chatting tomorrow, and I can send that along, and people can kind of sign up for her kind of full course and workshop in multi-level models. And then for the fall, I'm teaching an advanced research methods class that will meet through teams. It's an FSU class, but people are welcome to join it. Basically, how to write a grant where everyone has to write one for, it's like an R21 for the National Institute of Health. So it's a way to just get experience for those who haven't or want to refine or want to teach me, maybe. Here's how to write a grant, because for those who have written grants, been successful or struggled, which is me in many ways, the way you write a grant is very different than the way you write a paper. So there's a lot of considerations, and you're trying to sway people to say, give me money based on my ideas. So I'll be teaching a class that will run from end of August through end of November. It meets once a week. It'll be recorded, so if people are interested, I will let you know when I have that information, and I'll kind of have signups. Okay, so today is multi-level modeling, and you'll see that the data that we're working with this week is different from last week's data. And so I'm just going to go ahead and read that in. And then what you'll see, I'm actually going to open up that data just to orient us to the different variables that are in there, because it has implications for what we're doing. So this is cross-sectional data. And what we have here is a student ID variable, a school ID variable. We have 2 different classroom ID variables. So this is the teacher ID from 2nd grade. This is a teacher ID from 3rd grade. This is end of year reading comprehension scores at the child level. We have 2 dichotomous variables here that reflect whether the student's sex was male for 1, female 0, and whether the student was eligible for free or reduced price lunch. So if they were, it's a 1. If not, it's a 0. We also have child level vocabulary scores. And then this is a grand mean centered child level vocabulary score. This is the percent of students within a school that are eligible for free reduced lunch. And then this is a grand mean centered variable for free reduced lunch. Yeah, and I'm going to go through these in more detail as we go through the models. I just want to give you a high level overview. This is a group centered variable for vocabulary. So this is the raw score. This is the grand mean, where you're looking at how the student did relative to everyone in the sample. This is how did the student do relative to a group, in which case classroom. So this is a classroom-based deviation. This is a sample-based deviation. And then this is the percent of students in a classroom that were male. And then this is a centered, a grand mean centered percent of kids in a classroom that were male. So what you can kind of see from even just this is that this classroom had 50% students that were male. Their centered value is 0, which means that the mean is 50%. So that's kind of unsurprising. So that's the data set we're going to work through today. I'll be explaining lots of things, probably skipping over other things, messing up on who knows what, but we'll get moving. You'll see there is a longitudinal data set I created, but it's hashed out here because that's what we're going to maybe think about next week. All right, so to start, as we've talked about regression, whether it was kind of multiple single level regression or quantile regression, what we're always looking at there is the effect of X on Y. And so we're trying to understand the strengths, basically the magnitude and the direction of a relation between some predictor and some outcome. And so simple linear regression is super helpful for that, as is multiple regression when we have multiple covariates. But part of the issues with single level regression is that there are assumptions being made about the independence of observations. And so there's an assumption that each observation is independent of the other. But when you have nested structures like kids in classrooms or classrooms in schools or kids within treatment centers or otherwise, there's a whole host of different ways that individuals are clustered together. You violate that assumption. There is a shared environment such that if you have 10 kids, 5 are in classroom 1 and 5 are in classroom 2, those kids within each of those classrooms are more likely to be similar to each other than they are to be similar when you pool them all together. And the reason is that when you have nesting of kids in a class, those classrooms are taught by teachers. And so the teacher in classroom 1 may have 20 years of experience and has a particular method of teaching, whereas the teacher of the second classroom, it may be his or her first year teaching and has their own perspective on teaching and experience. And the teacher knowledge and teacher practices all influence how the child learns. And so we want to account for shared environments wherever individuals are clustered together. And so the way that we have to model that is different than a single level regression, because if we look at something like reading comprehension, we can't simply say that the reason that kids may differ in their reading comprehension is simply due to child level factors. Yes, kids may differ in their reading comprehension because of vocabulary or because of demographic factors or home factors, but there's also some of the reason why those kids vary in reading is because of instruction. And so multi-level models are ways for us to disaggregate the amount of variance in our outcome like reading comprehension that's due to between child differences versus between classroom differences or between school differences or between district or state. And so multi-level models kind of let you be able to take the error that would be tested in a single linear regression, and it actually then subnotates it by saying that there are errors at each level. And those errors have certain distributions and associated variances that we can then quantify how much of the variance in something like reading is due to kid differences, class differences, or school differences. And we can then also appropriately model variables at the level in which they were intended. And so if you have a child level variable like vocabulary, or a classroom variable like percent of students who are male, or a school level variable like percent of individuals who are eligible for free reduced lunch, you can look to say how much of the variance at each level of analysis did you explain by your covariates. And so when we included each of these predictors, we can always be looking at, is this an important predictor to understand child, classroom, or school level differences? And when you build the models out that way, you can have better implications about the malleability of your outcomes, about how you might treat schools and classrooms differently in terms of instruction or policy when you have a better understanding of those things that have an effect on the outcome. So one of the ways that I like to start looking at the importance of using a multi-level model is just through some simple plotting. So one of the things we will do first, once you read it, read the data in. I'm not going to go through all the details of these commands in ggplot. We're going to start doing that in a couple of weeks. But I want to very basically plot the relation between vocabulary and reading comprehension score and get some kind of linear model to give me a line of fit. And so you can see that there's a moderate, if not strong, relation between vocabulary and reading comprehension, such that higher vocabulary scores tend to be associated with higher levels of reading comprehension. So that's interesting, and we can certainly model this in the single level regression, and we would be perfectly fine. But when we understand that there are contextual variables like schools, we could actually then kind of plot the data differently to say, do the slope lines vary across schools, which is essentially saying, does the relation between vocabulary and reading comprehension vary according to the different schools? So you can rerun this code right here, where we're going to get kind of color-coded estimates of the relation between vocabulary and reading comprehension with school level fit lines. So this is actually just starting by color coding everyone. And so the different colors just kind of aligns in some ways to the different schools. I think there's 130 different schools, or maybe 150 schools in this data set. And so greens tend to correspond to the same school. So we can then overlay, this is where we'll actually overlay the individual regression lines. And we want to look to see, does the slope line differ across schools? And the answer is yes, right? So you get some schools that are more similar, like these two, that have very similar kind of steep slopes. And that can be compared to this school, which has a little bit of a weaker slope. You actually have this school right here, which has an inverse relation between vocabulary and reading comprehension. You have this school right here. It's kind of hard to see, but if I were to blow this up or make the lines bigger, you can see this school right here. There is no relation between vocabulary and reading comprehension in those schools. So this is showing that there are enough differences in terms of the slope of the line that might suggest we want to do a multi-level model. But like most things, it's actually an empirical question. Whoa. Obviously, I messed something up there. Okay. Oh, there we go. Let me back up here. Sorry about that. All right. So it's an empirical question as the extent to which a multi-level model is going to be useful for us. And I would encourage you to read. There's a lot of differing statistical philosophies about whether you should do a multi-level model or not. Some people would say that it depends on the interclass correlations. And so if the percent of variance at your upper level unit is less than like 5% or 2%, you don't need to include it. Some say if you need at least 5 upper level units to justify using a multi-level model. I would encourage you to read some of Dan McNeish. He's out of Arizona State. He is a stellar statistician, and he's done some fantastic work about the importance of multi-level models for small sample sizes when you have small cluster level ends. And so, read that literature if you're not up on it. It's really good in trying to understand when you should or should not use a multi-level model. Almost any time that there's clustering, I'm going to use a multi-level model, because beyond thinking about decomposing the variances to different levels like classes, schools, or students, it's really to be able to get unbiased estimates of your standard errors. And so especially if you're doing randomized control trials, or you're thinking about the implications of slope coefficients as a malleable factor, you're trying to judge the importance of those slopes based on the p-value, which is related to the standard error. And if you don't use a multi-level model, whether it's by specifically modeling the different the clustered nature through specific random effects, yes, that Daniel McNeish. If you don't specifically use either a multi-level model or use cluster-corrected standard errors, which basically means you're going to hand correct or use a sandwich estimator to give you the right standard errors that acknowledge clustering, you're going to be making it's kind of a false discovery rate. You're saying something significant when it's actually not, because your standard errors are biased, because you're not accounting for the fact that the data are nested. All right, so that being said, let's call up, we're going to talk about the LME4 package. And so what we're really going to be focusing on today is lmer. So lmer is the linear mixed effects models. And so we're doing linear mixed effects models. There are other versions within LME4 of what you can do. And so there's Glimmer, not to be confused with the main character, one of the main characters in She-Ra. The Glimmer does generalized linear mixed effects models. So this one is just doing the linear mixed effects models. And basically the form of doing the multi-level model in R is simply this. It's the object, if you're going to save everything to an object like we have been doing this summer. So the object is equal to, your main command here is lmer. And then we specify this portion of the model just like we did with the regression. You have the dv, you have the tilting, and then you have your list of IVs that are separated by plus signs in an additive model. And then you can use asterisks for creating or pipes to create interaction effects, or otherwise you can use the asterisks there. It makes it easier. But then at the end of your listing of fixed effects, right? If you have your independent variables, those are all fixed effects in the lemma statement. Then you have to add in your random effects. And the way you add in your random effects is by, you have this parenthetical. So you specify your dv, you specify your iv, and to that, to the list of all your independent variables, you're going to add in all of your random effects. So if you have something like kids that are nested just in schools, then you would have one parenthetical where you specify the intercept, and then you pipe it, and then you put in the school level ID, which so random effect 1. If you have more than one random effect, you just list out in an additive framework all of the different random effects you have. So if you have kids nested within classes, nested within schools, you list out your fixed effects here. Then you would add in intercept, pipe, and then your teacher ID, plus intercept, pipe, your school ID. And then if you had districts, you just keep adding in. So every single additive effect, every single random effect gets added in an additive manner. So I'm going to be redundant by saying you added it in additively. Boy, say that 5 times fast. Okay, so we specify the dependent variable, we list the fixed effects that we want to use as predictors, and then we put in the random effects where we're saying, where do we believe a random effect exists? So minimally, you believe that your intercepts randomly vary across your upper level units, whether it's classes, schools, or something else. After you add in your fixed effects and your random effects, you specify your data set. If you're using population weights or sample weights for any reason, you can do weights equals the weight var. And then you actually have to specify if you want restricted maximum likelihood or not. So the default in this case is that restricted maximum likelihood is true. So if you don't do anything else, it's going to be using restricted maximum likelihood and not maximum likelihood. And this is really important. In many of the models that I run, I have to override that default. I don't want restricted maximum likelihood. I want full information maximum likelihood. And there's a couple different reasons for that. One is that restricted maximum likelihood, it gives you unbiased estimates of the variance parameters, but it also it separates out the fixed effects and the random effects, and it doesn't actually allow you to compare your models to each other. So REML transforms the data when you're estimating each model. So the likelihood estimate that you get from one model to the next, those aren't comparable to each other. And so REML kind of separates the fixed and the random parameters, whereas FIML does not. So FIML can result in a little bit more of a biased estimate of the variance components, but we're interested in fixed effects and random effects. And often we're trying to figure out what model fits best, whether we're adding in fixed effect terms or looking at the appropriateness of the model given a random effect term. So if you're thinking about fixed and random effects and you have missing data, overriding the REML command is important and using REML equals false. If you're only interested in the random effects of the model, then you can do REML equals true. There's also different guiding language as to whether you use REML or FIML based on sample size. And so I've seen quite a bit out there that when sample size is smaller, when upper level unit sample size is smaller, REML is better. I tend to hedge on FIML. And so I'd encourage you to kind of read up on that on your own a little bit. But you'll see for all these models, I'm basically doing REML equals false. So again, we name the object. The command is lmer. We specify the dependent variable. We list out the fixed effects that we want here. We then add in the random effects that we want. We specify the data set. You override the command for REML equals true if you need to by specifying REML equals false, and you can put in weights. There's other things you can put into this statement, but this is by and large what you will use 90% of the time is this functional form of lmer. So let's go ahead and jump into this. So go ahead and load up LME4 as well as lmer test. So what's interesting about LME4 is that by default, it will not give you p-values. I think it doesn't give you p-values or standard errors or I think t-tests or z-tests for the coefficients that you estimate in the model. And so you actually need to use the lmer test package that will then piggyback off of the LME4 results to give you the full kind of substantive results. So if you want kind of formal hypothesis testing for any of your multi-level models, you need to have LME4 and lmer test both loaded up before you run your models. All right. So with these two things now loaded, I'm specifying an unconditional random intercept model. So what I want to start with, and then just a forecast, we're going to cover 2-level models and how you specify those. We're going to cover 3-level models, a cross-classified model where kids are kind of crossed by grade. So you might have 10 kids, all of whom were in the same 2nd grade class, but then when they went to 3rd grade, 5 of them went to the same 3rd grade class. 2 others might have gone to a similar 3rd grade class, and then 3 more went to their own 3rd grade class. So kids are cross-classified. They didn't all move from the same 2nd grade class to the same 3rd grade class. So their kids' scores are crossed. It's not nested because 2nd grade is not nested in 3rd. Classrooms are crossed by each other. And then within that, I'll be talking a little bit about centering a little bit. So we'll see where we get over the next 40 minutes. So I want to start in a basic 2-level model, considering kids that are nested within schools, and kind of looking at how we kind of build the right model that has the right type of how we treat the intercept. Do we treat it as random? Do we treat it as fixed? And Amy, can you post? I don't know if you were able to correct it. If you were, I see Randy is asking a question about our tools for 4.0. If you revert back to 3.5.3 or an earlier version, that may take care of it. So if you had success there, Amy, maybe you could let us know, and maybe that helps Randy as well. So we're going to start with an unconditional random intercept model, right? Which is your very basic. There's no covariates in the model. We just want to be able to look at the mean intercept, the standard error and p-value, and then we want to be able to look at how much of the variance is due to child differences and school differences. And so one of the key things for multi-level models in R is you are only specifying the upper level units in your random effects. You do not need to specify your lowest level, because when you look at the multi-level model conventioning, the lowest level is the residual. It's the residual. And so you have the residual at level 1, and then you have your upper level random effects. And so the residual is going to be produced automatically. You don't need to specify the actual random effect for students. That's going to be estimated at the end. So in an unconditional random intercept model, I'm just specifying the object here as UC for unconditional. It's an unconditional school model with a random intercept. So that's just my labeling convention there. I'm specifying my dependent variable here as the SAT10. And then you'll notice I put a 1 here. So 1 in this model, that means intercept. So I'm basically saying estimate the intercept for the fixed effect. I want the grand mean SAT10 score for all students across all schools in this data set. No predictors. And then I add to that this random effect. Okay, so I'm saying here, the random effect for it being a 2-level model, this is the school ID. So I want to be able to get an estimate of the variance for schools according to the intercept. So onto the left of this pipe, so the pipe is what separates the clustering unit or the upper level ID in terms of school from kind of the fixed effect that you expect to vary across levels of that ID. So we have a one here that says, get the estimated grand mean intercept across everybody. And we want to test for the extent to which that intercept randomly varies across schools, okay? And then you'll see as we build these models, there's some variance that I'll kind of explain. All right, so we have our equation. We want to look at the grand mean intercept for reading comprehension. We want to test the extent to which that intercept significantly varies across schools. This is the data set. And then I want to use full information maximum likelihood. So I'm specifying REML equals false. All right, so let me do, and then to get a summary of the data, we just do summary. I don't know why I didn't put that there before. All right, and so then here's the result. So this is saying that the grand mean intercept for all observations, which is 8,400 individuals across 140 schools, the grand mean intercept is 564. We've got the standard error, the degrees of freedom, the t statistic, and the p-value, right? So based on the standard error and estimate, we can say that 564 is reliably different from 0. Okay, so that's good. Now we want to be able to get, that's the fixed effects part. So that's actually what's great about this output. I kind of skipped ahead a little bit. So let me get back to orienting us to the output. When you do the summary, it's going to tell you what it was you specified. So that's a great way to be able to actually check and make sure that the model ran was the model you wanted. You get fit indices, which are going to be useful as we look at model comparisons. So as we add terms, whether we add fixed effects or random effects or both, we can be able to compare the AIC, BIC, deviance statistic, et cetera, to be able to look at improved model fit. And then it gives you kind of the scaled residuals and the mean, and then the main pieces we want to see here, which are random effects and fixed effects, right? That's the main thing we're doing with multi-level models. If we were only ever interested in fixed effects, we could just be doing single level regression. We wouldn't care about the random effects. But because we think that the fact that kids are being nested within classrooms, the fact that we see that the relation between vocabulary and comprehension results in different slopes when we actually model these individually at the school level, it suggests that there's something happening of kids in schools that we should account for. So we want to look at fixed effects and random effects. So the fixed effects tells us the mean reading comprehension, and now the random effects are going to actually tell us is there variance at each level, what the value of the variance is, and then we can use that information to kind of decompose the variance into, oh, that's why I put it down here. We can decompose the variance into the portion that's due to schools and the portion that's due to classes, to students. And so to do that, the interclass correlation here is just a function of taking each of the groups. In this case, this is the school ID. And so the variance that's associated with schools is 171.1. The variance associated with students is 1956.3. That's the residual. And so we don't need to put in the student ID. You just have to know what your lowest level unit is, right? Because up here, we specified that the ID of the clustering unit of schools, we did not specify students. You just need to know that your observations at the lowest level are students. And so the amount of variance that's due to schools is 177. The amount of variance due to students is 1956. And so we can actually look at we can create a ratio to say how much of the total variance is due to schools. So to get the ratio of school variance to total variance, we take this 171 and we divide it by the sum of, we take the 177 and divide it by the sum of 177 and 1956, okay? The total variance is the sum of all of your variances. So school variance and residual variance are our two components. And so to get the proportion of variance due to schools, we take the 177 and we divide it by the sum of the variance components. And so in this case, we see that accounts to 8%. So 8% of the total variance is due to differences between schools. And then, right, we can just take 1 minus that value. And that tells us how much of the variance in reading is due to student differences. So this is essentially saying the mean score, mean reading comprehension for these 8,000 students is 565. And kind of 92% of the reason, in some ways, for lack of a better phrasing, 92% of the variance in reading comprehension is attributed to differences between students. Only 8% is due to differences between schools. Now, for some people, you may balk at me saying only 8%. And that would be a good critique, because it's not about, well, only 8%. It's like, wow, 8% of why kids differ in their performance on an end of year test is simply because of the school that they're in. And so we would then want to think about, well, could we explain how much of, could we explain why, or how much of the variance that's due to schools could be due to school level factors? So we could say, how much of that 8% can we explain? How much of the 92% can we explain? So that's where adding covariates helps us to understand what we can explain for whom. This command right here, this ANOVA, this actually allows you to be able to compare the extent to which adding a random effect improves the model. And so what this is doing here is saying, it's saying you've specified a model that includes the school level random effect, which is right here, and then it compares it to a model with no random effects, essentially a single level regression. And it's comparing the log likelihood value right here. And it's doing an empirical test to say, does your model fit improve by treating the data as having a random effect due to schools? And in this case, the p-value is less than 0.001. And so including school level random effects is important for this model. So that's an unconditional model. And that's where we should almost always start, is before putting any predictors in the model, you want to be able to ascertain what's the mean, and how much the variance is due to each of your upper level and lower level units. In this case, we have kids nested in schools, and we're seeing that the mean score is 565 approximately, and 8% of the variance in all of these scores is due to school differences. 92% is due to kid differences. So then we can try to model covariates to explain variance at the school and child level. So what I'm going to do first is add in a level 1 predictor. So that's this model right here. And so what I'm going to do is test a random intercept fixed slope model. So that's this one here, C1 RIFS random intercept fixed slope. And all I'm doing here is expanding on what we did in this line. And so here I have the DV and the intercept and the random effect. I'm doing the exact same thing here. I have the DV, I have the intercept, but now I've added in a slope term, right? I want to look at vocabulary and how vocabulary predicts reading comprehension. So what I'm going to get out of this is an estimate of the intercept. I'm going to get a slope coefficient, and then I'm going to get a set of random effects. I'm going to get I'll get a variance estimate for schools and a variance estimate for kids. And then I haven't changed anything here. And the reason that the slope is fixed is that in this statement right here, I've only specified a random intercept, right? Slope is not in this term. If I wanted a random slope, I would say 1 plus PPVT. Now we're gonna get there, but I'm just showing it to you now, so when you see it in another moment or two, you won't be surprised. So that's what makes this a random intercept fixed slope, is in the random effect statement here for schools. I've only said intercept should be random. I've not said PPVT should be random, because that is our slope coefficient. So let's run the random intercept fixed slope model. And so what you can see here is, again, we get our fixed effects, we get some random effects. And so for the fixed effects, you can see that we're getting some of the scientific notation, so we have to move this over. So the mean here is 436.2. We're going to talk about that, why it changed so much, in a minute. We get a slope coefficient of 1.35. And so PPVT is significantly related to reading comprehension. And then we can actually, let me see if I do this. I do, but we'll get there in a second. So we get those fixed effects. So vocabulary is significantly related to reading comprehension. And then we have these random effects here. One quick note before I move on is I have this other model here called ALT. What you can see is that this is another version of the random intercept fixed slope. You can see here that I took the 1 plus out of this model, okay? And so once you start adding in slopes, you no longer need to specify a 1 in your model. It's only in the unconditional model that you have to specify the 1. Now you can do it just like I did here, right? In this model, I did 1 plus the PPVT. But if I run this alt model, you'll see the result is identical. Let me blow this up a little bit. So here's when I put in the 1 plus PPVT, here's when I take the 1 plus out and I have PPVT only. And so to streamline your model building, once you start adding in covariates, you do not need the 1 plus. You still need the 1 in your random effects, right? So you can see why you have a 1 here. It's because in an unconditional model or in a conditional model, the 1 is implied. So the extended form of this is 1 plus. I'm just choosing to omit it because I don't have to have it. But you always have to have, if you believe that there are random intercepts, you have to have the 1 in the random statement. Okay. Okay, so I have this further down, but I want to actually just show this real quick. Let me go back to the summary here. All right, so the summary said in the original model, this is where we had like these 2 variance components, and we said 92% is due to kid differences and 8% is due to this. But when we compare those numbers to what we saw in the conditional model, you can see the numbers have changed. This is no predictors, right? The variance at the child level is 1956. And when I put in vocabulary, it's now dropped to 1604. That's what we expect, right? As you add in predictors, your variance should be reduced. And this is what allows you to come up with like a pseudo R squared. It's to be able to say how much of the variance at each level was explained by the coefficient. And to do that, you do the variance from the unconditional model minus the variance in the conditional model, right? So this is how much variance with no predictors at the kid level. This is the amount of variance when we put in a predictor. And then we divide that by the unconditional model variance. So by including vocabulary at the child level, we explain 18% of the variance in kids' reading comprehension scores by the kids' vocabulary scores, okay? That's a pseudo R squared statistic. We can do the exact same thing at the school level. We can say how much of the variance in school level differences is explained by child level variables. So we take the 177 in the unconditional model, we subtract from that the 113 in the conditional model, right? Because that's when we include vocabulary. We see that the amount of variance due to schools has dropped, or the variance at the school level has dropped. So when we include vocabulary as a predictor of kids' reading differences, it tells us that we explain 18% of why kids differ, but it also tells us that we can explain 36% of the reason why schools differ. So a little bit more than a third of the reason why schools differ in their average school level reading comprehension is because of the average vocabulary at the school level, at the child level, sorry. And so kid differences in vocabulary explain why schools differ in their reading comprehension. So that would be a useful statistic to be able to report in a paper. So although you expect there to be, for the biggest impact of your child level variables to be on child level outcomes, it can always have an effect on your upper level units, just like we have here. So including kid level vocabulary actually tells us something more about schools on the surface than it does about kids. But here's the catch, all right? The amount of variance that was due to schools was school ICC equals 0.08, right? And student ICC was equal to 0.92. Well, R squared equals 0.18. Student R squared equals 0.3. Whoops, that's backwards. 6.8. All right. So the intraclass correlation says almost all the variance is due to student differences, and about 10% is due to schools. The R squared is larger at the school level than it is at the student. But what this is saying is that we've explained a third of this number, right? So we've explained 30%, 36% of the reason why schools differ, but the reason schools differ overall is only 8% of the variance. So one way to say this is that we have explained 36% of 8%. And conversely, when we say that we've explained 18% of the student level variance, we've explained 18% of 92%. All right, so that's a little bit of a kind of messes with your head a little bit, but I'm going to leave that there. And then if you want to also kind of like type that into your code, that might help if you're not familiar with multi-level models. If this is old hat, I apologize, but for those who may not be aware, I think that that's a useful thing to be thinking about. Because if we conclude we're explaining more variance at the school level than at the kid level, then we might actually overestimate the role of vocabulary at the school level, when in fact, 20% of 0.92 is 18%. A third of 8% is like 3%, right? So we could drop this down from, it's explaining 3% versus 18. So this 18% matters more overall than the 36 does. So it takes a little bit of math in order to be able to get these things explained the right way. I know this is a lot. Hopefully, if you listen to this again, or you do some research on your own, you'll maybe find a better explanation. I'm trying to kind of zip through this a little bit. All right, so that was the random intercept fixed slope. Well, what if we flip this around a little bit? What if we instead said, I want a fixed intercept with a random slope, okay? Well, so what I would do, like I showed before, is, the model we had was the 1 plus. So if I wanted a random intercept and a random slope, I could say 1 plus PPVT, because this is the intercept that I believe varies over schools. And then I also think vocabulary varies over schools, so I could do 1 plus. But if I think that the intercept is fixed, I need to change that to 0. Okay, so I still have the same command and the same fixed effects. I still have reading comp as the DV, vocabulary as the IV. But then when it comes to the random effects, I'm fixing the effect of the intercept to be the same across schools. I'm not letting it randomly vary. I only want vocabulary. I want the slope to randomly vary across schools. Everything else is the same. So this is fixed intercept, random slope. We can run it. It's going to hate us for doing that. There's some warnings, but you can ignore those. And then you get this result here. So notice that you get a student level residual, and then you get a school level random slope. So whether that's useful to you or not, I would encourage you to have a very strong maybe theory of why you would want a fixed intercept. And so you actually still get the random. This is the random intercept for kids, because again, you're not specifying it. So why would you think that reading comprehension doesn't vary across schools, but the relation between vocabulary and comprehension does vary across schools? It's a little wonky to think about, but you can still specify that. So here we're getting a slope coefficient that randomly varies across schools, and then a random intercept that only varies across students. So we say that that reading comprehension varies between students, and the relation between vocabulary and reading comprehension, or actually the effect of PPVT on student outcomes varies across schools, but reading comprehension does not vary across schools. That's what this model does. And then here is the random intercept, random slope model, where now we have the same dependent variable, independent variable for the fixed effects, and then I've added in 2 random effects. So the intercept, the slope, we can specify that. It's going to think for a minute or two, and then we get the fixed effect estimates here. So the mean, so what this is saying, this is the mean SAT-10 score when PPVT is 0, right? We get the slope coefficient here. They're both significant. And then here are the estimates for reading comprehension intercepts that vary across schools, right? So it's 399. We get the reading comprehension estimate that varies over students, which is 1594, and then we get a slope coefficient that randomly varies, but it's minus 0.02, so it's 0.0488, so a very small amount that is actually due to slope differences over schools. And in fact, you get what this core over here is the correlation between intercept and slope coefficients across schools. So this negative, this strong negative correlation is saying school level intercepts are negatively correlated with school level slope. So a school with a high reading comprehension estimate intercept has a lower or smaller slope coefficient. So schools with lower reading comprehension intercepts have higher slope coefficients for PPVT. And so let me actually plot that. Okay, so we have these fixed effects here, and we have then the random effects here, and we can actually plot the individual slope and vocabulary coefficients across schools using this command. So this is saying plot the coefficients from this object, right? So because we ran the lmer and stored it in this object, we can pull the intercepted slope coefficients for each school in the model. So we're saying plot the coefficients from the random intercept and random slope model at the school level. And so each of these dots represents a school. And so down here, this is a school that has an intercept value of about 410 with a slope coefficient value of PPVT of almost 1.7. But you can see as the estimated intercept values increase, right, along the x-axis, so as each school level intercept increases, the value of the slope coefficient is going down. That's the negative correlation right here. Okay, so this is not the correlation between vocabulary and reading comprehension. This is the correlation between the intercepts and slopes at the school level. So it's something different than what we were observing. But one question that you might ask is, are these intercept values actually plausible? Okay, so if we went way back up here to the unconditional model, the mean for the mean reading comprehension score for the sample was 564. What we see along here for all the school level estimates is that the intercept values are 410 to 470. So a question could be like, do these make sense? And so if I actually look at the get the mean and the standard deviation for the SAT-10, which is what this is associated with. So the mean is 565, which is what we see right here, right? So the grand mean estimate in the multi-level model with no predictors is aligned pretty well to the sample mean, and the standard deviation is 46. So the fact that we're actually getting these estimates of 410 to 470, that's a few standard deviations below the actual mean, right? So the question is, why are we getting that? And that actually gets to this kind of rabbit trail on centering. And so for those who have taken multi-level model classes or who have not, I would really encourage you to do some reading on centering. Centering matters quite a bit. And there's actually 3 different ways that you can center variables, right? So you may have heard of centering related to regression. That's the idea of having a meaningful 0. So when you have a dichotomous variable like sex, where female is 1 and male is 0, that variable is centered, right? There's a meaningful 0. 0 means that there is a default category, and then you have a fitted deflection from that, which is the 1 value. And so without any kind of centering in your continuous measures, it's assuming that the 0 point actually reflects 0, right? So in this model up here, where we're looking at a slope coefficient of 1.35 and the estimated intercept is 436. It's again, the estimated intercept value when PPVT, when vocabulary score is 0. So intuitively, this actually makes sense, okay? So if you think back to this original scatter plot, let me see if it will do it without blowing up. But the original scatter plot that showed the relation between vocabulary and reading comprehension, there was that kind of like moderate, right? Here's this moderate to strong association between vocabulary and reading comprehension. If we go all the way down here, because these are standard scores, that's what the SS is. If we kind of get all the way down here, you can see that even someone with like a 40, someone with a 40 on the PPVT, we're getting down around a score of 400, right? So if we assume that someone has a PPVT score of 0, it is plausible that their estimated reading comprehension would be 436. So that's why something like centering could be important for the way we think about interpreting these measures. So there are 3 types of centering you can do. There's not centering, so you can have uncentered measures. You can have grand mean centering, and you can have group mean centering. So I think what we'll probably do, because there's still a lot of code here, we'll probably go ahead and we'll probably talk about centering, and then next week, I think I'm already deciding it's probably best for us to do a second week on multi-level models. And this would actually be some good reading to do on the side if you have time, is to read on centering, because centering is actually a really complex issue. Let me do the easy one. Whenever you're doing a multi-level model and you have level 2 and level 3 variables, you should always center your predictors. You always need a meaningful 0 for your upper level units, because otherwise it's very complex to be, if not, well, it's not impossible, but it doesn't really make sense to have uncentered measures at each level, because you're trying to account for average performance in your X's, in your measured variables at each level. So if you have like the percent of kids at a school that's eligible for free reduced lunch, you want that 0 point to be meaningful, so you can look at as free reduced lunch increases by a unit, there is some type of related or associated change in estimated reading comprehension. If it's uncentered, you get kind of these conflated or confounding interpretations that are very challenging to navigate when you include multiple predictors in the model. So for upper level units, you should always be thinking about probably grand mean centering. And so grand mean centering is just looking at, it's adjusting the estimates for kind of the level specific means. So for a child level, centering is just looking at the individual performance relative to the entire sample's mean. So for PPVT, if the mean is 100 and a child has a score of 105, then their grand mean centered value is 5, because they scored 5 points above the mean. And you would do that for each of your measures at each of your levels. If you have a teacher level measure like teacher knowledge, you would want a grand mean center at the classroom level and look at how teachers are doing compared to teacher level means. And then at the school level, you would look at school deviations from school level means. And so each variable can be centered at each clustering level's mean. So, and that's grand mean centering. So again, grand mean centering is where you're just kind of like adjusting those different values according to sample level means at each level of interest. Group mean centering is where you look at deviations as a function of a clustering measure. So you can do group mean centering for, I think, for lower level units. I can't remember. Can you group mean center? If you group mean center at the higher level cluster, yeah, there is no group mean centering at the higher level cluster, because that's the highest level, right? So if you have 10 kids within a school, you could, or let's say you have 20 kids within 2 schools, 10 are in school 1 and 10 are in school 2. Grand mean centering would be looking at how all 20 kids kind of differ from all of each other, right? You get the mean of the 20 kids and you look at the deviations from the mean of those 20. Group mean centering would be separating out each of those 10 kids and having each separate set of 10 have their variables centered around their school level performances. So rather than taking a grand mean and saying, I want to look at how each child deviates from the mean of 20, you'd instead, for group mean centering, I want to see how each of these 10 students deviate from each of those 10 kids' means within a school. But you can't group mean center at the highest level unit because you only have you have a sample of 1 of each school, right? You can't group mean center a school variable when there is only 1 representation of that school at the school level. So wherever you have individuals nested within a cluster, you can group mean center. But group mean centering can hold challenges. So group mean centering, it holds constant, kind of the level 2, let's say the level 2 means and level 1 predictors. But what's really hard is that people really differ about whether you should really ever group mean centered. So you have some people that give kind of examples and have done simulations to show why group mean centering may matter at level 1 or level 2. Other people say you should never group mean center. What I tend to do is I always have my upper level units centered at the grand mean, and then I leave my lowest level units uncentered. Part of it depends on what I'm wanting to do with my results. So something like the result right here, where the data are uncentered, I can still talk about the strength of the coefficient and talk about increases in expected reading comprehension given vocabulary, but I have to be really careful about what I say about kids' reading comprehension. Because if I'm trying to say something about kids' estimated reading comp, this isn't a true reflection of the sample mean. It's a reflection of the estimated reading comprehension when vocabulary is literally 0, and 0 for vocabulary means there is no vocabulary in that child. So instead, I want to be able to hedge and think about what's the estimates of the slopes, what's the strength of the relations. I may not give as much value to interpreting the intercept for those types of models. And part of that can be when I ultimately do some plotting of coefficients, there's implications there for whether you group center, grand mean center, or leave things uncentered. So what I'm going to do very quickly, we're going to pick up on this next week. I actually kind of want to do a quick example. Let me see if I can show it quickly before we have to kind of close here. All right, let me see. I'm going to do a grand mean based model. All right, so this is looking at the PPVT, where I'm not including the raw PPVT score from before. I'm now including a grand mean centered. So I'm looking at individual deviations from the full sample mean. You can see when I do that, the estimated grand mean is actually the same as it was before, 565, right? And so when we move the decimal over, this is the same as before, but that's because the data is now centered on the grand mean of the sample. So this is what makes sense. But there are implications here, because if I plot, remember before, let me do this plot up here. If I plot the coefficients from an uncentered model, we kind of see, well, there's variability in the magnitude of the PPVT coefficients according to their estimated intercepts when the model is uncentered, right? When the PPVT is uncentered, you get all of these different values because you're not kind of conflating individuals' performance on the PPVT relative to the sample. Everything is just uncentered. If I plot the coefficients from a grand mean centered model, you get something like this, right? Because you get the whole range of coefficients, but it automatically constrains that estimated intercept to be the same for all individuals. So again, it gets to what is your research question going to be, or what kind of hypotheses do you have in terms of why you would center or not. So we'll get into this a little bit more next week. I know I did a lot of setup this week, but I think that's kind of important for maybe some of these multi-level models in terms of thinking about components, building the model, random effects, fixed effects, ICCs, and percent variance. So next week, we should be able to get into, we'll finish up like a specific discussion about centering, and then we're going to get back to the modeling. And in that, we're going to look at interactions, cross-level interactions between variables, adding in school level effects, looking at interactions, doing 3-level models, and then getting into cross-classified models. So what's great is you actually have all the code. And so if you want to tinker on your own, you are, of course, more than welcome to. And so probably what that means is we won't get into growth modeling or generalized linear mixed modeling, but that's probably something that Betsy is going to handle, and she will teach it much better than I will. So I hope this was interesting, enjoyable, complex, befuddling, other multisyllabic word here. I will get this video up shortly. And I think I also have to put the quantile regression one up as well. So thank you thank you, Constance, for putting that. I think that's like a chapter or paper. Yeah, that's a great paper. I would strongly recommend that. Thanks everyone for joining, and I will look forward to seeing you next week.